Alright, in this video we study the mean value theorem and its implications and applications. Okay, let's start. Suppose we have a function that is differentiable and let's pick 2 points along the graph of this function. Let's say this point and connect these 2 points. So we have a straight line like this. And the mean value theorem says there is at least one point on this graph where the slope of the tangent line at that point is equal to the slope of that given line. So in this case, this tangent line, the slope is equal to the slope of this line. Okay, that's what the mean value theorem says, basically. So we are going to prove this theorem, but before that, we first prove Rolle's theorem. Okay. That's an easier version of the mean value theorem. Rolle's theorem. So this theorem says the following. Suppose f of x is a continuous function. Continuous function on a closed interval between a and b. And also assume that this is differentiable. Differentiable on the open interval between a and b. Okay. And also assume that the value of f of a is equal to the value of f of b. Okay, and these are the assumptions. Then there exists some point C in the open interval between A and B such that f prime of C is equal to 0. Okay, and you can see that this Rolle's theorem is a special case of the mean value theorem. So let's visualize this case. So we have a function f of x such that f of a is equal to f of b. So this is one example of such a function. Okay, so if this is the case, then there is some point c, let's say maybe this or maybe this, such that the derivative or the differential coefficient is equal to 0. That means the tangent line is parallel to the x-axis. So this is the situation Rolle's theorem is referring to. So let's prove this, and we consider 2 cases separately. First, f of a equal to f of b are the global maximum and the global minimum at the same time. Maximum and minimum. In this case, then f of x is a constant function. Therefore, the derivative is always 0. So this x can be anywhere in this interval. Okay. So second case means 1 is not the case. So otherwise, that means otherwise f of x has a local maximum or minimum. Local maximum or minimum. So, and if the function takes a local maximum or minimum value, then at that point, and we have seen that the derivative at that point x equal to c, f prime of c is equal to 0. because it's a maximum or minimum, a local maximum or local minimum, then the derivative should be 0 at that point. And we are done. Next, let's state and prove the mean value theorem. Mean value theorem. Okay, so f of x is a continuous function on a closed interval between a and b, and also differentiable, just like Rolle's theorem, on the open interval between a and b. Okay, then there exists some point c in the open interval such that f prime of c is equal to the slope of the line connecting a, b, and f of a and f of b. That is f of b minus f of a divided by b minus a. So this is the slope. So if we have a function like this, let's see. So this is point A, and let's say this is point B. So we are considering only this closed interval. And if we connect these 2 points, we have this slope. Okay, so this difference is b minus a. This difference is f of b minus f of a. So the slope is this. And then there exists some point C, let's say, where the slope of the tangent line is equal to the slope of this line connecting the 2 points. So let's prove this theorem. And to prove this theorem, we use Rolle's theorem. But to use Rolle's theorem, we define a new function. So let g of x be f of x minus f of x, wait a minute, f of b minus f of a over b minus a times x minus a. Okay. So if we define this function, then g of a is f of a minus f of b minus f of a over b minus a, and a minus a. So this term disappears, so this is equal to f of a. Okay, and g of b is f of b minus f of b minus f of a over b minus a, and this is b minus a here. So this and this cancels, so we have b f of b minus f of b minus f of a. But this f of b and this f of b cancels, and negative times negative is positive, so we have f of a. So that means g of b is equal to g of a. And obviously, since f of x is a continuous function, and this is just a linear function, so it is continuous, and the sum of continuous functions is continuous, and of course f of x is differentiable, and linear function is differentiable, and the sum of two differentiable functions is also differentiable. So this function g of x satisfies all the conditions required for Rolle's theorem. Therefore, we apply Rolle's theorem. That is by let's say by Rolle's theorem. Rolle theorem. There exists C in the interval between a and b such that g prime of c is equal to 0. Okay, so what is g prime? So if we differentiate this function, we have f prime of x, and for the linear part, we have negative f of b minus f of a over b minus a. So if we substitute x equal to c, then we have g of c, f of c, and this is equal to 0. Therefore, f prime of c is equal to the slope of the line connecting between a and b. And we are done. Now, from this mean value theorem, we can derive a number of interesting and useful corollaries. And the first one is this. If, suppose f of x is differentiable. Differentiable on some interval I, open interval I, between a and b, let's say. And f prime of x is identically equal to 0. That means for all x in the interval, f prime of x is equal to 0. Okay, so this means everywhere the derivative is 0 on this interval. Okay, then the function f of x is actually a constant function. That means there exists some constant, let's say real number, such that for all x in the interval, f of x is equal to c. So this means f of x is just a constant function. Okay, so this says if the derivative is always 0, constantly 0, then the function itself is a constant. So maybe this seems trivial, but let's try to prove this. Okay, so first of all, pick any constant c from the interval and let capital C equals to f of lowercase c. Okay, so this defines a constant. Now, if x is equal to c, then obviously f of c is equal to c, so that's fine. So let's suppose f is less than c. Okay, then by the mean value theorem, there exists some d in the interval, so we are considering this between x and c, such that, let's see, f prime of d is equal to f of x minus f of c and x minus c, right? So from this, we have f of x equals to f prime of d times fx minus c plus f of c. But by assumption, this differential coefficient is 0. So it's 0 everywhere. So at point D, it is of course equal to 0. Therefore, f of x is equal to f of c. Okay. So, and same, we can show similarly for the case where x is greater than c. Okay. So in any case, we can show that f of x is equal to f of c. So, which is equal to a constant c. So f of x is a constant everywhere in the interval. And the next consequence of a corollary of the mean value theorem is the following. As usual, we assume that f of x is continuous on a closed interval between a and b. Let's call it I. And also differentiable in the open interval between a and b. Let's call it I circle. Okay. Now, if for all x in the open interval, f prime of x is positive, then, so if this is the case, then f of x is strictly monotone increasing. Okay. And similarly, so this is 1, and similarly, if for all x in the open interval f prime of x is negative, then f of x is strictly monotone decreasing. Okay. We will prove only part 1 for strictly monotone increasing function, but the second one is very similar, so you should try that yourself. Okay, so in order to prove that a function is monotone increasing, it suffices to show the following. So if C and D so for all C and D in the open interval, C less than D implies f of C less than f of D. So if this holds for any C and D, then we can, actually this is the definition of monotone increasing function. So let's do that. So let's pick C and D like this. And by the mean value theorem, there exists some, let's say, t in the open interval such that the following holds. F prime of t is equal to f of d minus f of c over d minus c. Okay, and from this, we have f of d minus f of c equals to f prime of t and d minus c. And now, suppose if c is less than d, then we have d minus c is positive, right? And also, f prime of t is positive by assumption. So by assumption means we have this assumption, right? For any point in the open interval, the derivative is positive. So this is positive. So therefore, this is positive times positive. That means this is positive. So therefore, f of d minus f of c is positive. Okay, therefore f of d is greater than f of c. And we are done. And the next corollary of the mean value theorem is related to local extreme values. Suppose f of x is at least twice differentiable. And assume that f of c is equal to 0. So the point C is a stationary or critical point. Okay, then first, if f double prime of C is positive, then x equal to C is a local minimum point. And 2, if f double prime C is negative, then x equal to C, this point, is a local maximum point. Previously, we have seen that this condition, that is C, the point C being a stationary point, is not sufficient for the point C to be a local extremum point. But together with this condition, or this condition, now we have all the necessary conditions for a point to be a local extremum point. And as usual, we only prove the first part, and the second part is similar, so you should try that yourself. Okay, so let's do that. And by definition of the second derivative, we have this. x going to c, f prime of x minus f prime of c over x minus c. So by assumption, f prime of c is 0. So this is equal to just f prime of x over x minus c, which is equal to f double prime of c. Now, let epsilon be this f double prime of c. And remember the definition of a limit. And so we have this limit. So that means there exists some delta that is positive such that if x and c are close enough, that is, the difference between x and c is less than delta, then this implies that the difference between this and this is less than epsilon. So that is this f prime of x divided by x minus c minus f double prime of c. So this difference is less than epsilon. Okay. By the way, this is positive by assumption, right? So for the second case, we should put this is negative of this. But anyway, so now we have this. So this implies, in particular, negative epsilon, this x minus c and f double prime of c less than epsilon. So let's consider this part. Okay, from here we have f prime of x over x minus c is greater than f double prime of c minus epsilon. However, we define epsilon as this. So this is actually 0. Now we consider two cases. First, x is in this interval between c minus delta and c. Okay, this delta, by the way, is this delta. Okay, it is guaranteed to exist. So if this is the case, then x minus c is negative. And since this is positive, that means f prime of x is negative. And this means f of x is monotone decreasing in this interval. Decreasing. So this is according to the previous result we have proved in this video. Monotone decreasing on this interval, c minus delta and c. So that means for all x in this interval, c minus delta and c, we have f of x is greater than f of c, because x is less than c, okay? Because it's monotone decreasing, we have this. All right. Next, second case, x is in the opposite of c. That is between c and c plus delta. In this case, we have x minus c that is positive, and therefore f prime of x must be positive because their ratio is positive. So that means f of x is monotone increasing in this case. Monotone increasing on this interval. Therefore, for all x in this interval, c and c plus delta, that means x is greater than c. And that means f of x is greater than f of c. So either case, we have f of x greater than f of c. Okay, so that means let's say this is c and this is c minus delta and c plus delta. We have situation like this. Okay, so in this interval, it's monotone decreasing. So f of x is greater than f of c. And in this interval, f of x is increasing, so f of x is greater than f of c. So either case, f of x is greater than f of c. That means f of c is a local minimum. Okay, therefore, f of c is a local minimum. And we are done. Okay, so next we define the convexity and concavity of a function. And we say function f of x, we assume appropriate continuity and differentiability as usual, is said to be convex at x equal to c if the following holds. So that is, there exists some delta that is positive such that if the difference between x and c is between 0 and delta, then f of x is greater than the tangent line at c. So that is this. Okay, so visually this means such a case that, such as this. So suppose this is x equal to c, and the tangent line at c is this. So if we draw this tangent line, then around x equal to c, so if we take small enough interval around c, then the value of the function is always greater than the value of the tangent line. So this is what it means for a function to be convex at x equal to c. And similarly, we define concavity. So we say function f of x is concave at x equal to c. And this means, by definition, there exists some delta that is positive such that if the difference between x and c is between 0 and delta, then the value of the function f of x is less than the value of the tangent line at that point. So x minus c plus f of c. So it's just an opposite of convex case. That is, the function looks like this. And let's say this is x equal to c. And the tangent line at this point is something like this. So around x equal to c, so if we just look at some small region around x equal to c, then the value of the function is always below the tangent line at x equal to c. So this is what it means for the function f of x to be a concave function at x equal to c. Now we have another corollary of the mean value theorem that is related to the convexity or concavity of a function. And we assume that f of x is twice differentiable at least, and of course accordingly it's continuous. And if that's the case, then if f double prime of c is positive, then f of x is convex at x equal to c. And similarly, if the second derivative at c is less than 0, if it's negative, then f of x is concave at x equal to c. And as usual, we only prove the first part, and the second part is similar, so you should try that yourself. Okay, so for proving this, we define a new function g of x. That is the difference between f of x and its tangent line at x equal to c. So that is, so the tangent line is f prime of c, x minus c, plus f of c here, right? So if we have a line like this, and if c is here, then the tangent line is this, right? So this g of x means the difference between this function and this tangent line, okay? So that means so at x equal to c, this g becomes 0. So, and we show that this is the minimum value of g of x. Okay, so first, let's differentiate this. G prime of x. So if we just differentiate this, then it's f prime of x. And from this part, we have negative c prime, negative f prime of c, which becomes 0 at, so g prime of c is equal to f prime of c minus f prime of c, which is 0. And g double prime of x is, so this is constant, so we just have f double prime of x, and at x equal to c, this second derivative becomes f double prime of c, which is positive by assumption. Here's the assumption, okay? So this is positive. So we have two conditions satisfied. The first derivative is 0, and the second derivative is positive. So that means g of c is a local minimum. And that implies, therefore, if x is close enough, sufficiently close to c, enough to c, then we have g of x greater than 0, right? Because the g of c is 0, by the way, as we have explained. So if we put x equal to 0, this part is 0, and f of c minus f of c, so that is 0. So this is always greater than 0, therefore f of x is greater than the tangent line. So f prime of c and f minus c plus f of c. And therefore f of x is convex at x equal to c. Okay, let's see an example. Consider f of x that is equal to exponential of negative x squared. And we try to find that where this function is convex or concave. Okay, so first, let's differentiate it. So we can use the chain rule, and if we differentiate this, and we get, exponential function doesn't change, but something inside exponential function, we can differentiate again here. So we have this negative 2x and exponential of this. And we differentiate it again. And we can use product rule, of course. And so and this, and negative 2x and negative 2x. Again, we have this. So we have, let's see, so 2x squared minus 1 exponential of negative x squared. And if we solve this equation, so let this be equal to 0, then we have x equals to plus minus square root of 1 over square root of 2 as the solution, right? Because this is always positive, so this can be 0 if x is this. So if the absolute value of x is greater than 1 over square root of 2, then this is positive, right? So if the absolute value of x is greater than 1 over square root of 2, then f double prime of x is positive. And if that is less than this, then it's negative. So in this interval, or rather it's a union of two intervals actually, the function is convex, and in this interval, the function is concave. And if you plot this function, it looks like this. So it's an even function. So it's symmetric around x equal to 0. So it's symmetric. And so around here, it's concave. But around here or here, it's convex, right? So where this convexity changes, is this. So it's negative 1 over square root of 2 and positive 1 over square root of 2. So in this interval, it's concave. In this or this intervals, it is convex. So in this example, this point, plus minus 1 over square root of 2, are some characteristic points of this function, and they are at these points, the convexity of the function changes. And these points are called inflection points. Or sometimes some people might write inflection points. Okay. Okay, that's all for this video. See you later.